My topic is vector search and state-of-the-art retrieval for generative AI apps. So RAG has come time and again in today's session as well. So I think most of you are already familiar with it. Okay, so first, let's see some of the uses of LLMs, right? So these are some of the famous LLMs, ChatGPT, Gemini, and Anthropic Claude. So people generally, they use them for, let's say, question answering, or we put a chunk of the text and ask for the summary, or to extract some information from the text. So these are some general uses, and pretty much everyone uses these tools these days. So, but there are some issues with LLMs. So if you can see the text in the right, so first one is data cutoff, right? So the first question I've asked is, why was Sam Altman fired from OpenAI? But since the data cutoff is January 2022, the LLM ChatGPT in this case is not able to answer this question. And second case is of hallucination, right? So what do you know about the statue of Abraham Lincoln in Kathmandu? I mean, there's no such statue in Kathmandu, but it is just giving the answer, right? The statue of is a unique monument, blah, blah, blah. So there is this thing. And other issues are with bias. So we are pretty familiar with the Gemini controversy a few weeks back. So these are all the issues with LLMs. Like companies, they are working to solve this, but they haven't been solved yet completely. So, and the other issue is with private data, right? So we don't want the companies to access our private data, but we want to use Gen AI on our private data to get some, let's say, to make some decision making or to get the information in short amount of time. But there are some issues. Generally, the most common use is passing the data as prompt, and the issue that occurs with prompt engineering is context length. So let's say if our data does not fit in the context length of the LLM, then we won't be able to use it. Other issue is with cost, which is on the basis of number of tokens and the processing time. We could solve that by fine-tuning the models on our private data, but there are some complexities in terms of the compute required and the technical complexities. And again, the data keeps on changing, then we need to keep on fine-tuning it time and again. To solve these issues, the technique is retrieval augmented generation. So is there anyone who is not aware of RAG, like completely new to RAG? Okay, so that means most of you are familiar. So I'm going a bit fast, so please stop me if it is not that clear. So first step is indexing, right? So in RAG, what we do is we use off-the-shelf LLM, and then we use it to talk with our data. So we don't train the model on our data, we just indexing means just storing it somewhere so that it is easier to retrieve and query on top of it. So the first step we do is indexing. Let's say you have some private data. It can be HR policies or your financial documents or health documents, anything like that, which you cannot expose to outer world, to private, let's say public companies or some other providers. So we store it in some manner that is like efficient for retrieval. So the first step is indexing. Let's say we have N documents as shown in the right. So we may store them in a way that makes it easier to retrieve. And some example of storing is, that should be a vector indexing, or we can store it in the form of graph or Elasticsearch. So we can use any form, but vector search is quite popular with RAG, and we'll see that later on why that is the case. So first step is to index the data so that it is easier to retrieve. And second step is once we index the data, so that is a one-time process until the data changes. It is stored in, let's say, some server. It can be managed or self-hosted, something like that. And the second step we do is retrieve, right? So let's say you have a document of your financial 2022 financial documents, and then the user might ask, what was the profit or what was the profit in 2022? So that query we need to match that query with the documents we have indexed earlier. And once we match that, we get the top K from that list. So out of N documents, we get the K documents that are the closest one, and then we formulate the answer based on those documents. So the third step is generation. And in generation, what we do is we use the retrieved documents to answer the question. So if we have the context might be 5 or 10 sentences that was retrieved from the index, and this is a simple prompt which I have written over there. We can tune it to get the better results. So we just ask the LLM. It can be OpenAI, Gemini, or some open source LLM, anyone. And the prompt can be answer the given question. So we place the question there using the context. So we give the context, right? So what it enables is, if we are not able to do this, then we just ask the question, and if the model had not seen that particular data, then it would either say I won't be able to answer this, or just come up with answer like it did earlier in statue of Abraham Lincoln in Kathmandu, right? So but since we are providing it with question and the context, it will try to formulate the answer based on that context. That means we don't need to fine tune the model, or we don't need to pass entire document to the prompt to formulate the answer. We can just pass the relevant chunk of text that we have retrieved from the index vector search, and then we can use that to formulate the answer. So that means our answer will be grounded on the context of the actual data we have. So this is the main benefit of RAG. So these are some applications. So first one is recommender systems. We can index the items, and then we can compare the embeddings of different items and then recommend the related ones. And the later other three they are kind of related. So QA engine, we can think of it as ChatGPT like chatbots. So search engine, Perplexity, and Bing Copilot, they are quite famous. And in dialogue systems, so kind of chatbot. Let's say you are you want to chat with customer service of Doras, then what they will do is they will index their entire documents, and then when the customers they ask for the questions, the earlier process of index like retrieving the related chunks and then formulating the answer. So that process will be the process, and then it will be able to generate the answers. So these are some applications. So again, RAG has been, there has been quite a lot of research going on RAG. So it is kind of divided into three paradigms. So naive, advanced, and RAG. So naive is the most basic one, where we just index the sentences or the particular chunk of text. So that depends on our chunking strategy. And it might have some issues like low precision, recall, and then outdated information means the information which we extract from the DB or vector DB, that might not be enough. So those issues might be there. And advanced RAG, it will improve on top of naive by doing like strategies on different chunking strategies and storing some kind of metadata that will be helpful to answer the question. So in retrieval, we could again fine-tune the embedding model, because that might not be useful. The already available ones might not be useful for our data, and we might need to fine-tune those. And in post-retrieval, we could do re-ranking of the like related chunks or compressing the prompt, so to remove the unwanted information, all those sorts of things. The advanced one is modular RAG. Here we could integrate search engines, techniques like hypothetical document embedding, where instead of matching the query, we generate the hypothetical document that is close to the query, and we match those documents to get the related relevant chunks, and like dividing the query into multiple parts to get sub-queries. So these are all sorts of things. So like I have attached the references. You could go through those if you want to explore this in detail. And once we build the RAG system, we need to kind of evaluate it, right? So because we won't be sure how the system is performing. So there are some metrics that have been developed to evaluate RAG. So context relevance, whether the context is relevant to our query or not, faithfulness, and then answer relevance. So these three are called qualities, and the bottom four, they are the abilities, like ability to reject noise and negative information, and integrating information from multiple sources, counterfactual robustness. So these are the metrics against which RAG systems are evaluated. And then in terms of tools, like doing this manually, it is not possible. So TrueLens and RAGAS, these are some of the tools that help us automate this process. Any questions so far? So this is kind of an introduction to RAG. So if not, then okay, so we discussed RAG, right? So we could index document in any form we want. So it can be SQL databases or Elasticsearch, simple text files, but why vector search, right? So whenever you see RAG, vector search comes as a friend of RAG. Like if there is RAG, then automatically we see that vector search is being used. So the main use of vector search is to capture semantic similarity. So on the right side, there are 3 documents that are related to some vacations. And then in the left, we can see 3 queries, right? So again, the similar kind of query can be asked by different people on different tone, right? So if we're doing some kind of text matching, then if the text do not match, then we won't be able to get the relevant chunks, right? Because although the meaning is similar, like comparing the text, it won't give the relevant chunks. So vector search, it enables us to capture the semantic similarity. And how is it able to do this goes back to the strategy of training like embedding models. So if you are familiar with, let's say, BORT or sentence transformers, then they are trained in such a way that similar sentences having similar meaning will have similar kind of vectors. So yeah, we'll be able to get the relevant chunks. So the first process will be to get the end documents that we have in our knowledge base. Then first we'll chunk them. It might be fixed length, sentence level, or paragraph level. So that needs to be experimented with. Then we'll select an embedding model. So embedding model means it will convert the text to the vectors. And then it can be either open source or self-hosted. And then again, there will be factors we need to take care of: the context length of the model, dimension, and like comparison qualities, all those things. And once we pass the end documents, we'll get the end embeddings using that embedding model. And we'll index those in VectorDB. So the popular ones are Pinecone and Chroma. Again, the options for us is to either go with open source, self-host, or use the managed solutions. So Pinecone is managed, and Chroma is the open source, which you can self-host. And then once we index these documents, so it will be our database or knowledge base. So after that, the step of query will start. Again, we'll need to use the same embedding model that was used while indexing for query as well. So we'll generate the embedding of query, and we'll compare that query against the DB, so which we have done indexing earlier. And the matrix can be either cosine similarity or Euclidean distance. So that will compare the query embedding with all those embeddings which we have in our DB, and it will give us the candidates. Let's say K is our parameter. So if we want top 5, then it will give us the top 5 closest candidates. And then once we have those K candidates, we'll merge it with the prompt. So prompt can be used to kind of structure the answer, or to use some kind of guardrails, or those sorts of things. And then utilizing the prompt and candidates together, that will give us the answer as we want it. So this is the kind of a RAG and vector search procedure. Yeah, so almost a minute to have left. Okay. So any questions so far? Yeah.
How can you determine the chunk size?
Okay, so chunking. So first, the chunks should fit inside the context length of LLM, right? So if we are using LLM of 512, then we are kind of limited by the number of tokens we need to use. So we cannot go beyond 512. But within 512, one strategy might be to chunk at the sentence level and use the earlier and the preceding and the succeeding sentences as metadata, so that we'll have a longer context. So that can be one strategy. In earlier, people also used to kind of chunk at the fixed interval and then do the overlap. So if we have 512, then let's chunk at 500 tokens, but between first, second, third, we could try to overlap 100 or 200 tokens so that the context is maintained. Again, that might have advantages and disadvantages, because there might be kind of like abrupt ending and abrupt starting, right, without any meaning. So ideally, it is a experiment kind of thing. But one thing which I have seen earlier is like splitting at the sentence level, but after merging using the context before and after the sentence, so that we'll have a larger context and the relevant chunks. So we'll see that in demo as well. Okay, so this is the vector search process. Then there is some algorithm called HNSW, hierarchical navigable small words. So it is kind of a proximity based graph. So again, So once we have vector DBs, the next step is to compare the query embedding with vector DBs, right? So we cannot just go on. So we might have millions and billions of vectors, and then comparing the query with each and every vector serially, that will consume a lot of time. So again, that might give the results, but from the efficiency point of view, that is not kind of good. So HNSW is the current state-of-the-art algorithm for indexing and querying. So I've just mentioned the querying part over here. Indexing part is not included. So what it does is it is based on two things called probability skip list and navigable small worlds NSWs, and then these two are combined to give HNSW. The basic idea is we'll not compare each and every vector serially. We'll just kind of maintain some data structure while indexing the document, and then while comparing them, we'll try to limit the source space to a minimum, but again we will want to get the relevant results. So it might not get 100% recall, it might drop a bit, but the trading off between efficiency and the accuracy, it comes ahead of other techniques. So the first thing to understand over here is probability skip list. So it consists of multiple linked lists. So if you can see there are 4 layers, layer 0 till 3, and then let's say we are searching for 11, right? So we start at the top layer, and then we'll compare the query. So for in this case, for us the query is 11, and once we get 11, then our source will complete, otherwise it will go on and on. So at first we'll compare it with 5, right? Because we're starting at the top, and the next index after starting is 5, so it does not match. And then after once it compares with 5, then we'll go to again to the next index. So this is the ending index. So it hasn't been found so far. Then we'll go to the bottom layer, and bottom layer again it will compare with 5, then it will compare with 19, right? In this case 19 is greater than 11, and we are storing it in sorted order, so we'll be sure that we won't get it after 19. Again we go to the bottom layer in layer 1, and then after following the similar step, we'll get 11 over there. So this is probability skip list, just for the refresher. And the second idea it is based on is navigable small worlds NSW, and it is also a proximity based graph. That means you can consider all these circles as the vectors of different document we have indexed, and then they will be kind of the neighbors of those nodes will be the nodes that are closer to them. So in this case, yeah, each vertex has degree 3, so that means it cannot have more than 3 neighbors. So it will be connected to the closest 3 vectors or vertices in the graph. So this is a navigable small world. And the problem with NSW is that there is a high chance of getting stuck in the local minima, because we'll start with one entry point, and if we do not get further friends or neighbors from a particular vector, then we'll have to settle at that vector. And HNSW, it will kind of merge the probability skip list and NSW to combine or to make the graph at hierarchical level. So we'll start at this entry point, and if we do not find the matching ones, we'll go to the bottom layer, and again if not found in this, then we'll go to the bottom layer, right? So layer 0 will be sourced at the end and layer 2 at the beginning, and once it, so similar process of NSW will be followed, but in this case it will be organized hierarchically, and yeah, it is HNSW. So this is just for the query purpose. So if you want to follow, like go through the indexing setup, then you can follow that link. That is quite helpful. And the next thing is demo. So this is Stanford AI report from 2023, I think. So I've tried to index it, and then okay. So here are 2 queries for indexing and querying, but let's just go to the index. So I have used Pinecone to index this data, because Pinecone is managed solution. We don't need to do local setup and all those things. So for experimentation purpose, it is quite easy. And if you see here, So the method I have followed here for indexing is, I'm indexing at the sentence level, but while fetching the data, I'm storing 2 sentences before this index sentence and 2 sentences after this. So for the, if we get the top 5 sentences, we'll have total 15 sentences in total. So that will kind of have a larger context and we'll be able to answer the questions. So the embedding model is OpenAI's ADA 002. It is 1536 dimensional. Yeah. So if you see here, the original text is the text that has been that is passed to the embedding model to generate the vectors, and all these numbers, they are the vectors that have been computed for that particular text. And in window, it consists of the preceding 2 sentences, the sentence that has been like that is being indexed from the embedding, and then the 2 sentences after that embedding. So for every sentence, we'll have 2 before itself and then 2 after that, total 5 sentences in total. So yeah, this is the pinecone index. Sorry, zoom. Yeah, is it okay? Yeah, so basically here, these are the main, like the core thing, these are the vectors and rest are the meta information, and we'll be able to utilize those metadata in some way while generating the answers. Yeah. So this is the indexing part. Let's just see some hyperparameters. So yeah, this is the main thing that I would like to share. This is the querying one, and here this is the question which I have asked to the RAG system. So list down some text to image models. So since this report has been written in 2023 or beginning of 24, but and I'm using OpenAI's LLM for the generation part, it will not have access to the later models, right? So for this question, so this is the cosine similarity. So, and then this is the text that has been fetched from the index, and yeah, so the answer, and I have like written a prompt in a way that it will give us the answer in bullet form. And then if you can see here, Google's Imagine, it was released in 2023 kind of thing, and then it is not included. So if you ask ChatGPT about Google's Imagine, it will just come up with some fake, like not real answers, but it has been able to get these tools from the earlier indexed documents. So here are some other things I have asked, like who are the authors of the report, which is the most in-demand field of AI, and then what is the global investment. So these answers, like I've tried this and it is getting the correct ones for this. So yeah, this is from my presentation. If you have any questions, then I can take them, or we can wrap up.